All right, I promise this one will be quick. So I don't want to to talk much more about the different things, but in the objectives I had strains. So how do you compute strains? And then I'm just gonna do again. I'll try to just do definitions. So there's a few things. So obviously f is the most important object. In continuum mechanics, maybe in continuum mechanics, it's definitely the most important object for defining the local deformation. And we saw that it has information about changes in length, changes in area, changes in volume. But typically you don't really use f that much, and you're more used to things like strain. So we're going to define a few other tensors that come up quite a lot more, which are derived from f. So C, which is, we already introduced this one, is f transpose f. This is called the Wright-Cauchy-Green deformation tensor. Wright-Cauchy-Green deformation tensor. And that one contains similar information to f, but it has a few other properties. So it's a symmetric second order tensor. And then we'll see that it doesn't contain information about rotations. And that won't make full sense right now, but it has some nice properties because it's symmetric. It's part of your homework. It has something called the spectral decomposition. It has a set of eigenvalues, a set of eigenvectors that can be chosen to be orthogonal to each other, so you can have an orthonormal basis associated with C. So it has some bunch of nice properties. And it also, as I said, it gets rid of rotations, but that we'll do in the Tuesday lecture. Another one is B, which is f transpose, and that one is called the left Cauchy-Green deformation tensor. And then it's also symmetric. And then it also has nice properties. C and B also have some nice relationship between one and the other, because you can see one is f transpose f, the other one is f transpose. You can think of something that can take you from C to B, for example, some relationship or some things that are common. In terms of strain, there's E, which is the Green-Lagrange strain, and that's C minus I. This is called the Green-Lagrange strain, which is closely related to the usual strain that you know, the approximation. So this is closely related to the little epsilon, which was 1/2 of gradient U plus gradient U transpose in linear elasticity. And then one more that I'll introduce is this Euler-Almanzi strain, which is 1/2 I minus B inverse, which is called the Euler-Almanzi strain. And that's it. Those are 4 definitions of strain tensors. I'm not gonna do much with this right now because I think it will require a little bit more information. I'll probably go back to these ones on Tuesday. So for now, just good for you to know that F is the most important object. It has all this information about how a cube deforms to this parallelogram, or how a sphere deforms into this ellipsoid. And so you can use F, but F has almost too much information, and these other C, B, E, or E are strains. So F is not symmetric, like you saw, and that's because it has information about rotations, which are not really important for deformation. So if you're just interested in basically stretching of things or strains, then you use C, B, E, or E, or little e, rather than F directly. So that's where it will come into play. But I